Hello, this is Team 27, and this is our ENME472 Report 3 Design Report. For this report, we continue to develop our initial concepts into a final design. From this, we have achieved the following. The lift can carry up to 40 pounds of trash on the platform and takes 30 seconds to go up and 30 seconds to come back down. The user only needs to lift the trash 21 inches off the ground to put it on the lift platform, as opposed to the over 3.5 feet that would otherwise be required. We can run the carrier at 1.5 miles per hour. We can load the carrier with 90 pounds of weight while operating at max performance. We can run the system for half an hour before needing to charge, and the carrier drive system was designed to be able to operate under a total weight of 170 pounds. The problem that we're trying to address is the challenges faced by elderly and disabled people during their everyday tasks. Specifically, we are addressing the challenges faced when taking out the trash. The biggest issues that arise are the physical requirements of this activity, such as lifting heavy loads and maneuvering large, unwieldy objects. In 2009, in England and Wales alone, people aged 65 or over accounted for 7,475 deaths as a result of an accident, of which 49% were due to a fall, and according to the Royal Society for the Prevention of Accidents, nearly 3/4 of falls among the 65 and over age group result in arm, leg, and shoulder injuries. As such, we will be addressing the dangers posed by the physical effort required when taking out the trash.
The design specification matrix details the needs that our product has to meet, the engineering characteristics that will measure these needs, as well as the methods we will use to test performance. On the left hand, we can note our priority customer requirements. These are that it helps the user with disposing trash bags, moves trash to the end of the driveway, and follows county guidelines for trash disposal. We've detailed in bold verbiage that identifies key product functions, as well as the engineering characteristics we can measure to achieve these requirements. The customer requirements outline our needs statement and guide several of our design decisions. For instance, we initially did not intend for our product to drop trash off at the collection site. Rather, it would sit idle until trash is removed from it. However, we found that in order to meet our third CR, we would need our product to be compatible with automatic trash collecting trucks, and as such, we implemented this function. On the right half of the DSM, we noted that our target values for our ECs. For our critical functions, these include a lifting capability of 40 pounds, with 20 pounds exerted max on the user end, 10 milliseconds of latency, an IP rating of 5.4, and an effective friction coefficient of 0.01 on the carrier platform. We identified testing methods for each of these design specifications, which include finite element analyses, prototyping plans, and hand-drawn free body diagrams and calculations. Some of these we will be sharing with you today.
There are two main subassemblies that are needed for our project. These were split into two teams so that work could be divided evenly. The first main subassembly is the lift and charging station. There are two main functions of this assembly: usage of a motor-driven pulley system to raise a platform designed to carefully hold a user-placed trash bag until it reaches the tipping height, where it will rotate, dumping the trash bag of max 40 pounds into the can. This entire process will be done with very minimal effort from the user, the simple push of a button located on the side of the lift. The second main function is the charging station, designed to interface with the mobility team's carrier system. This will have to be specifically dimensioned and calibrated to properly interact with the carrier system's onboard electronics and power system. The charging port on the station will have to line up with the location of the charging coil and battery on the carrier, and its setup location will have to be within 10 feet of a standard 120-volt wall outlet. The second main subassembly is the mobility system, consisting of one single carrier unit designed to safely hold a trash can of varying sizes, transport it to the desired drop-off location, and then carefully assist in the removal of the trash can from the carrier via integrated rollers. The mobility system requires specific components to operate properly. It needs two motors, one on each side of the carrier operating its two closest respective wheels. To provide the propulsion needed to move the carrier, we selected motors capable of providing us with adequate torque and speed values to hit our target requirements of moving a max weighted carrier at 120 pounds at 1.5 miles per hour. The carrier system may undergo some bumps or inclines during operation, so a fastening system will need to be in place to stop the trash can from tipping off the carrier platform. This will be done with 3 circular walls whose clamping distance can be adjusted by the user depending on the size of the trash can. The 4th wall will serve as both a fastener and a ramp, so the trash can be unloaded when it arrives at its drop-off location. This will be done with slight force from the user and the help of rollers underneath the can and on the ramp itself. There is also an onboard electronics and battery configuration to provide the necessary power and controls to allow the can to be operated by the user. Finally, the mobility team will have to design an RC controller and receiver to allow remote operation of the carrier system using a separate device. Originally, we considered a third team for obstacle detection and system autonomy, but we eliminated this after switching to an RC setup. Now the lift team will talk in more detail about their subassembly.
So first, I'm going to give an overview on the standard components for the lift subassembly. The standard components for the motor section include the motor, 3 motor couplings, 3 motor shafts, and 4 washers. After completing a series of motor calculations, we were able to find the correct motor based on torque and power needs for the function. The motor is considerably small, but works very well for this application. Originally, the spools were going to be a custom part, but after a lengthy discussion and finding an innovative solution, we decided to place 2 washers to the motor shaft and weld them together. The hole on the side of the washer is to secure the rope with a knot. For the lifting mechanism, the standard components are the crown rails, 6 crown roller bearings, 2 nut caps, the mounted pulleys, and the rope. The mounted pulleys we selected from McMaster-Carr are vertical lift pulleys with a max lift capacity of 600 pounds. The diameter of the pulley states that the pulley is compatible with 3/16-inch wire rope. To figure out the maximum load the ropes would have to lift and withstand, we completed the rope calculation shown on the left side of the screen. By maximizing the weight and the angle, we were able to figure out the maximum load of the rope to be 42.42 pounds. Combining both the rope diameter criteria given by the selected pulley as well as the maximum load criteria, we were able to select a rope from McMaster-Carr that has a lifting capacity of 450 pounds and works well in a hot and wet environment. To attach all the different components together, we sourced all the screws from McMaster-Carr. The Plastite screws are self-tapping and created with the intention to work on plastics such as HDPE. They are 1/4 of an inch in diameter and are 2 inches long. The eye bolts are the 2 places where the rope will connect to the bottom platform. The eye bolts are to be 1/4 of an inch in diameter and with a vertical lift capacity of 500 pounds, which is much higher than the 42.42 max load we need them to withstand. We have a lot of electrical components. They include sensors, buttons, and LEDs for the human interface. The contact switch is sourced from TE connectivity and will alert the system when the 2 lift platforms are at their lowest resting position. The angular limit switch from Sager will tell the system when the trash has fallen out of the top lift platform after reaching its max angle. The charging capabilities of the carrier revolve around the wireless charging coil. We completed a battery charging calculation with a 40% loss estimate to get us to 4.48 hours to charge fully. Now I'll go into the custom components. For the charging station, the function is to house all the electrical components in the carrier as a whole. The shape is robust and has basic rectangular geometry, therefore the part will be injection molded HDPE. The HDPE will have a UV stabilizer added into its composition to ensure no gases are released after being in direct UV contact for an extended period of time. The lift platforms must be able to withstand a 40-pound trash bag and not crack or have any deformation. The lift platform also has to have a very low coefficient of friction since the trash bag has to slide off of the platform when rotated. Therefore, we picked the ultra-high molecular weight polyethylene. It is lightweight, does not corrode, and easy to machine through compression molding. The cutout geometries can easily be accommodated by using this process. For the gray railing housing in the model, we're going to approach the part a little differently. Since stock aluminum shafts already exist, we're going to purchase them and use a CNC milling machine to cut them into the long rectangular pieces we need. Then we will weld them together. This geometry is unique since the railing has to fit into the housing very tightly with small tolerances. For the stoppers that are shown in the second picture, we'll be using UHMW as well. Due to the fact that it will be interfacing with the lift platforms on every lift, they cannot break or leave any abrasions on the surface. Therefore, they will be compression molded as well. For the motor housing, we need it to be a strong material that can withstand high temperatures. The housing has to be exactly dimensioned to fit around the motor. The motor has a unique shape, prompting us to make this a custom component and select bend stretch forming of aluminum.
The parametric design, the image on the left displays the lift platforms at the bottom position. This height will be what the user has to lift the trash into, which is 21 inches off the ground. The red rope is tied to the eye bolts on both sides of the lower carrier, wraps around the pulley at the top, and coils around the spool at the bottom. In the middle image, the lift platform is at its top position. As the platform comes into contact with the stoppers that sit on the right of the rails, the upper platform begins to rotate. The upper platform only has one roller as pictured in the image in the top right, and the bottom platform has 2, causing it to only move linearly. The chamfer on the bottom platform allows for full movement, which would be 11 degrees for the trash to slide down. This system is also adjustable because the stoppers can be moved every 8 inches to allow for varying heights of trash cans. Now moving on to the electronics portion of the lift, we will have wires connecting our motor, user button interface, contact switch, limit switch, charging coil, and power cord to the Arduino breadboard combo in the electronics housing. We included a mouse hole for the wires to go into the housing. This block of electronics will just be screwed into the charging housing for easy removal and replacement of any parts. We included a power LED button to signal when the system is on, and the device can still charge, but all the lift components cannot start up, which conserves energy. The lift up LED will be illuminated when the carrier is charging. This signals that the trash can is in the housing. Once the lift button is pressed, the motor will start lifting the trash up until it hits the limit switch in the top right image. This will trigger a switch in the code that reverses the motor and starts bringing it back down. The motor will shut off after the bottom platform hits the contact switch pictured in the bottom right image. Our wires will be wrapped in shrink wrap that will protect it from the weather. Lastly, these wires will be routed using adhesive wire holders. A big design decision we had to make was with the lift platforms. We chose the lightweight material of UHMW polyethylene to reduce the weight that the motor had to lift. The original image was a bulky piece of plastic weighing almost 30 pounds. This immediately caught our attention, and we performed a lot of FEA simulations to reduce the cost, weight, and material. We made cutouts to limit the weight even more. This resulted in a new weight of 8 pounds for the lower platform and 4 pounds for the upper platform. This greatly contributed to motor selection because we did not have to lift as much and the motor needed less torque. This allowed us to choose a more cost-effective motor.
So now we go to the mobility team to discuss their components. In regard to standard components for the mobility team, our key component used across the base plate, the ramp plate, and the static walls is the hollow rectangular aluminum tubing. The tubing can be found on the McMaster car website. We chose aluminum 661 due to its strength to weight characteristics, its corrosion resistance qualities, its machinability, especially with welding, since we'll be welding the base plate tubes and the walls together, as well as its heritage in many automotive designs. In regard to the reason they are tube-shaped, we wanted to minimize weight across the plate, so we decided to have a hollow center to keep our same shape profile while decreasing mass. More on that later, though. The next major component in the base plate assembly was the conveyor rollers. The conveyor rollers were selected as steel due to the steel's high strength and durability. The max weight capacity of 300 pounds was crucial for having a very heavy trash can load. Many other selections that were preferable, such as aluminum, were not able to support this capacity, as seen in the chart, where they have 16 pounds. We didn't choose stainless steel due to their high price in comparison and the limited selection for lengths. To account for the corrosion resistant properties, our steel rollers will have to be treated with zinc plating to account for environmental effects. All in all, the steel temperature range, weight capacity, and price made it a great selection. Some other critical standard components include the dynamic wall piece and our screw and nuts. We chose the dynamic wall to be an aluminum disc that is commercially available. The original idea was to use an aluminum sheet and then cut it down, but that would be expensive and wasteful. Additionally, we have to change our wall shape to a circle due to the rotating shaft, and this proved to save costs on additional bearings that we would have to use. The moving wall can be seen below, and how it works is that the user twists a bar that rotates the threaded shaft inwards, which clamps the disc to the trash can wall. The shaft is supported by a static wall, which has 2 threaded holes, and the disc is supported by 2 nuts. Also, due to the cost constraint, we had to choose a smaller diameter disc, but we accounted for the lost height with a taller static wall in order to achieve our target height of 9.3 inches to avoid tipping, which will be shown in our calculations later. Since this wall will be experiencing a component of the load of the trash can as it holds it in place, aluminum was a great selection due to its corrosion resistance, due to grinding on the trash can, its strength, its minimum weight in comparison to the steel. The wall will have a rubber coating on the clamping side to add extra grip to grab the trash can walls. Furthermore, the nuts and bolts were selected to be zinc-plated steel and stainless steel respectively due to their corrosion resistance, high strength, commercial availability, and low costs.
This is the moving ramp for the carrier. Much like the base plate, it's composited of standard parts. In addition to the parts we mentioned earlier, we're also using a ratcheting gear to lock the ramp in place and aluminum tubing, which will allow the ramp to pivot. Some components we'll be creating custom include the electronics housing. As the name suggests, this houses the Arduino, the H-bridge, and the RC module. This part isn't designed to experience any loading or stress conditions, but it will be exposed to sunlight, so we decided to create it using HDPE plastic. This will be done through injection molding, as the part has a very simple geometry, and this will allow us to mass produce. Next is the motor housing. As the name suggests, this houses the motor. Unlike the electronics housing, we expect this part to experience stress by weight load on the carrier as well as heat from the motors. We want a rigid material that will not warp under heat, so we decided to go with die-cast aluminum 6061. We have the battery mounts next. As the name suggests, this mounts the battery. This will be subject to heat stresses from chemical reactions in the battery, but not as much as the motors. So we went with injection molded ABS plastic, which will remain rigid under heat stress. We also have the roller mounts, and these will be supporting the rollers on the sides. These are small parts with tight tolerances, and since these will help bear the load of the trash can, we wanted a strong material, so once again we went with die-cast aluminum 6061. For the sake of time, some other components we created custom are the bolt to spin the moving wall, and we'll be using turning and grinding to manufacture this part for precise accuracy and fast and expensive production, as well as the socket for the bolt to interface with the wall. And here are the finished CAD models.
For our drive system, two 250-watt brushed DC motors were selected to provide the propulsion needed for the carrier system. The mobility team decided to go with a skid steer mechanism for our carrier. This was the least complex steering system to design that still fulfilled our needed product functions. With a skid steer system, the user can utilize two control joysticks that move forward and backward, one controlling the left two wheels of the carrier and the other controlling the right two. We originally were designing for the use of 5-inch radius wheels, but we chose to reduce the initial size of the wheels down to 3-inch radius to lower our torque value. The main downside to this is that it only gives us about a 1/2 inch clearance below the carrier, which could pose a problem for users that want to use the carrier system in uneven terrain, such as a grassy yard. We went with a chain and gear system to connect the driver gear on the motor to the driven gear on the wheels. We were initially considering using a belt system for this, but due to the price of the belts being about twice as much, we thought a chain would work fine. Here are the calculations for the motor. As we can see, we need 5 Newton meters per motor running at 84 RPMs, resulting in a required power of 44 watts. As shown in the previous slide, in order to maximize the torque and run the motor at our desired RPM, we will be using a gear reduction. 19 teeth on the driven gear and 22 teeth on the driven gear for a ratio of 0.864.
Here are the wiring diagrams for the carrier. Some important features to note here are that we intend to wire two 24-volt 8-amp-hour batteries in parallel in order to stack their amperage, running two 16-amp motors for half an hour. The motors are controlled by an H-bridge connected to battery power, and we have our wireless communications, motor control, and object detection handled by an Arduino, which taps into the battery power via a step-down voltage regulator. Our second design decision had us determine how long our ramp needed to be to make sure that no tipping occurred as it slides down. We took the moment about the corner of the trash can, bottom right in the image, and solved for x such that the sum of the moments in the positive direction are clockwise. Our known values are shown to the right. Since the rollers have a coefficient of friction of 0.001, we took this to be negligible. We found that our horizontal distance needed to be 0.21 meters or 8.2 inches. And using Pythagorean theorem, we found a ramp height of at least 9.764 inches is necessary to prevent the trash from tipping.
Our third major design decision was in regard to the base plate. Choosing precise dimensions in manufacturing processes was extremely critical for the design of the rest of the carrier, as well as the charging station. The base plate was the base of our model, so it'll serve as the baseline for all preceding dimensioning. Our first idea was to have our base plate model made of a solid aluminum member with a large cutout for the rollers and cutouts underneath the base. This proved to be ineffective due to the very expensive custom machined quote from Xometry, the impractical machinability, and the very heavy mass, which was over 100 pounds, and the additional cost due to the custom roller mount cutouts with tight tolerances. Due to this, our carrier would be way too expensive, so we had to think of a new idea. As a result, we decided to look for a more commercially available products that would be effective and came across aluminum rectangle hollow tubing from McMaster-Carr. The specs of these tubings were covered on slide 17, which detailed why aluminum was chosen. Regardless, how this improved on the design was that now the cost of the base plate was under $100, and that's compared to over $1,000 before. The base plate can be easily machined together by welding, and that includes the static walls, which can also be welded onto the base plate. And also the weight drastically reduced to 5.7 pounds, which helped the motor calculations to choose less expensive motors later on. After choosing the right material and the product to work with, making final design decisions for exact dimensioning and placements needed to occur. Some major tolerances that needed to be considered were with the tolerances listed in the spec sheet for the length/width of the tubing, as well as the general tolerance for die-casted parts, which is fairly minimal for our purposes. As a result, for our tolerance stack-up, we achieved a tolerance of 0.01224 for width and plus minus 0.036 for length. What we aimed was to make a 30 by 30 inch base plate so we can house a max trash can size of 27 by 27 inches for length and width. This allows us 1.5 inches on all sides to construct the moving sidewalls, which also need a stack up of their own in order to house smaller trash cans. So having some wiggle room in our outer dimensions were preferred. The main tolerance effects were seen in the cutout space, which was aimed to be 20 inches. The inside gap tolerance ended up calculating to be plus minus 0.12 inches. While that can pose an effect to our inside roller setup, due to the length of the roller being 17.4 inches with negligible tolerances, and the length between the die-casted mounts and the wall to be adjustable since they can be screwed in any spot, we accounted for the tolerances in our design by originally having a 1/8 inch gap between the middle inside part of the die-casted mounts wall and the roller's end piece, and that is where the roller mates with the mounts, so that we have the flexibility in case some of our parts came in oversized or undersized. This 1/8 inch gap on both sides will be enough to suffice a plus minus 0.12 tolerance indicated in our setup.
Here's the task analysis for loading the trash and taking it out to the curb. First, the user must set up the lift and charging system. When the system is delivered, someone from our team will be there to set up the system. But the steps that would need to be done are screwing all of the pieces together. The trash can would be put in the charging port to determine the appropriate height for the stoppers to be moved to. Then the cord should be plugged into an outlet. The power button would be pushed and the lift up button should be illuminated, indicating that the trash can is in the port. The second task analysis would need to be done by the user. They would walk their trash from their kitchen to the lifting station. The trash bag would be lifted up onto the top platform and the user would check that it is within the raised edges of the platform. The trash can should be in the station with the lid off, then the user can push the power and then lift up button.
This is the task analysis outlining the process of securing the trash can to the carrier and navigating it to the curb. First, the user must ensure the trash can is fastened to the carrier by rotating the securing walls and pushing the front ramp inward until the can is held down properly and does not shift side to side. Once the trash can is secured on the carrier mechanism, the user will then navigate the carrier to the desired drop-off location by use of a remote control device. The user must push both guidance joysticks forward to actuate each motor at the same time. After carefully navigating the carrier system to the drop-off location, the user will be ready to remove the trash can from the carrier. To drop the trash can off at the collection site, the user will have to stop any movement of the carrier once it has reached its drop-off location. Once the carrier has completely stopped, the user will have to loosen the carrier walls by rotating the handlebar mechanisms counterclockwise until the can becomes free to move left, right, and backwards. Once this has been done, the user will have to drop the front ramp via the release lever on the front of the carrier. Now that the ramp is down, the user can carefully push the back of the can so that it gradually moves across the rollers and down the ramp. The trash can should now be in a location where it is ready for pickup and it is time to move the carrier back to the docking station. Ensure the ramp is in its upright position by picking up the ramp from the ground and clicking it back into its securing position. Now the user must use the joysticks on the RC device to initiate motion back toward the docking station. Once the carrier is within a couple feet of the dock, they will have to rotate it by pushing only one of the joysticks down. The carrier must back into the docking station so that the charging ports and lift mechanisms line up. Now the user may turn off the RC controller and leave the carrier in the dock until it is needed again.
We used a simple risk assessment, which is similar to a rapid entire body assessment. The user must lift 10 to 35-pound trash bags 21 inches from the ground. I input that the user would use both hands to lift the trash so the weight is distributed between both arms. The task falls on the lower end of the moderate spectrum. The contributing factors to this tool are weight and position of the body. The worst factor is that their trunk and lower back are in poor position due to bending over to pick up the trash bag. Without our device, elderly people would be lifting up to 35 pounds of trash into a trash can that can be up to chest level, which would result in a high risk level. By lowering the rail to the lowest possible height, we are making it a lot easier on their bodies to lift the trash to an acceptable height. From report 2, we refined our specifications of our target population. We used the average height to find the average chest level of our users. This was used to determine where the user interface needed to go. The range of motion of arms, strength, balance, ability to walk, and dexterity all contribute to who can use our product and help with our human factors calculation.
Lastly, we'll be reviewing our DFMEA. For the navigation function, we identified 2 potential failure modes, the first being issues in the product hardware causing it to get lost. As we can see from our risk priority numbers, the highest risk scenarios are a drivetrain failure, and this is because of the high severity value, and an RC module interference due to its difficulty to detect. In order to prevent these from occurring, we created housings to ensure interference doesn't occur, and we'll be making the drivetrain easily accessible for repairs. The second potential failure mode would be environmental factors that cause the system to tip over while in transit. The scenarios with the highest risk for this category would be weather conditions, which have a slightly lower severity but occur more often, and physical impacts, which pose moderate severity and occur regularly. In order to work around these, we'll be carefully selecting the materials for the chassis to maximize strength, and intend to thoroughly prototype and test the carrier to ensure a suitable IP rating.
For loading the trash into the bin function, we identified the first failure mode to be the lift breaking or stalling. As we can see from our risk priority numbers, the highest risk scenarios are improper uses of the lift and impact the lift mechanism. To combat these scenarios, we've created an intuitive and basic product that will be given to the customers with a detailed setup and user manual. The lift is also to be built with strong and abrasive resistant material to keep the lift in good shape throughout its lifetime. The second potential failure mode would be the trash bag falling off of the lift platform. This cannot happen since one of our top customer requirements is to not have the user bend or lift any excess weight. To ensure this doesn't happen, we have created walls along the three sides of the top lift platform so the trash is secure when the lift is in operation. Charging the battery, we identified two potential failure modes, the first being misaligned coils. The risk priority numbers for this failure mode are fairly low. All three potential causes have a detection value of 1 since they can be easily fixed with an attentive user. For containing the overall misalignment of coils, we have provided an LED light that signals when the carrier is charging. The second potential failure mode is hardware failure. The risk priority numbers that are the highest are for faulty charging coils. Since the LED light only signals when the carrier is charging, the user might think the alignment of the coils is off rather than the coil being damaged. To combat this issue, if it was to arise, we have contained all the electronics housing in an easy-to-reach place to efficiently perform repairs when necessary.
The first aspect of sustainability in our design is the environmental impact. Our design utilizes already existing trash cans, preventing the need to buy new plastic cans and the disposal of old ones when the device is purchased. For its in-life use, our design can be used for things beyond just moving a trash can, such as aiding in moving heavy boxes or yard work supplies. The replaceable parts mean that if a single part malfunctions, the whole device need not be disposed of. The part can simply be replaced and the device can continue to be used. Additionally, parts can be recycled at the end of the product's lifespan to reduce waste. The economic impact of our design comes in the form of new manufacturing and assembly jobs that will be created in order to facilitate the manufacture of the device. The societal impact of our design will be the enhanced quality of life for elderly and disabled citizens. They will be able to conduct everyday activities without the need for additional assistance and without the danger posed by the physical activity required by taking out the trash. As mentioned before, nearly half of the 7,475 deaths in England and Wales in 2009 among the 65 and over demographic were due to accidents involving a fall. Beyond that, many others suffer bodily injuries as a result of strenuous activity and subsequently lose their autonomy and suffer a drop in their quality of life. Our design will eliminate multiple sources of these injuries and help prevent the loss of autonomy that many people suffer from. Additionally, our design will help those who have already lost some of their autonomy regain some of it by giving them a way to conduct daily activities that they would otherwise be unable to do. Here's our task tracking, and thank you for watching.